Hi, welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 2.3, Complex Arithmetics. In order for a complex number to be a valid number, it has to follow all the rules of mathematics. That includes all the basics of arithmetics, and I'm going to show you how they actually work. So in order for two complex number to add, it's actually pretty simple. So let's say we have an arbitrary complex a plus bi and add another arbitrary complex number c plus di. With that, you can just group up the real parts and the imaginary parts. So we have in the real part a plus c. In the imaginary part, however, we have b plus d. This works for all real a, b, and c, d. So with that said, we have two sums with the real part and the imaginary part, and so therefore the solution complex z is equal to a plus c in the real part and b plus d in the imaginary part. And you can notice that it is exactly the same as if you treat these as just normal algebra, say algebra of x, a polynomial that is. So you have constant a, constant c with a single order coefficient b and a single order coefficient d. You just group the like terms and you get the following after you factorized. And it works exactly the same as you would with algebra. That's why complex is actually not that difficult to grasp as a concept anyway. So now I'm going to talk about how the geometry of a sum of complex works. So if I call the arbitrary a plus bi as, I don't know, w, and c plus di, I'll call it as t, why not? So in order to add two complex numbers, you either first find the real part, add the real part, so you've got the real component of w. Let's use, I don't know, red. So I'll have w as red and I guess t as blue. So let's start w plus t. So w, a plus bi, is essentially a lots of bi, which is over here. And if I do c plus di with the blue one, let's say c is why not, c is here and d is here, so I have c plus di. So we've got 2 points on the Argand diagram. If I pull two straight lines from the dot to the origin, what I'm trying to do right now, essentially, that is the wrong thing to do. What I'm trying to do essentially is to create two factors, and I'm gonna tell you more about factors in a later video in the factors section. But for now, let's take a look. With this setup, we've got a plus bi as w and c plus di as t. And these 2 points, if we sum them together, it's as if you add the two factors together. So we can just copy this section, this length, over to the right, and let's denote z with green. That's a straight line function, not a pen. I want a pen. So if we denote c plus a on the axes as just a plus c, I guess, and if we denote on the imaginary axis b plus d, that would be roughly here-ish, b plus d. This will not be to exact scale, but if you do it on a graph paper, then it should actually make sense. So we've got z over here, and turns out if I pull another w from the end of t, I will get to z or z, and vice versa. You can do exactly the same with t added onto a, and you will get to the complex z. And this works for all addition of complex numbers. In the geometry terms, you can say that if you create a parallelogram from the two original factors, then the opposite angle, depends on how the angle works. Say if you give it directions, I'm gonna go back to black. If you give it direction away from the origin, then the angle from the origin to the resultant will be the sum of the two factors in the correct orientation. And if you subtract, it works the same as you do a factor subtraction, or it's just the opposite direction, and it would work the same way. So if I demonstrate with w take away t, then if I use cyan instead, then it should give me something like this. From just like from the point of my eye, it looks kind of the same distance, I guess. And so you should get a factor over here, or a dot over here, as w take t. And the direction is opposite, and they have the exact same magnitude or length. So that's summation, which is quite straightforward if you've done GCSE factors. To multiply two complex numbers, however, is a bit more tricky. You can indeed do the simple algebra method, which is to break the brackets open using either Krebs law or Krebs claw, or like FOIL methods. There are multiple ways of calling that, but I'm just gonna simply do the following: ABI plus CBI plus BDI squared. So this is the expression, but we know that I squared is -1 by definition, and so we can collect the like terms into the following: plus AB plus CBI, and that would be the solution to this multiplication. This, however, doesn't look entirely nice if you put it onto the Argand diagram using the factor kind of method that we use in the summation. It doesn't give you anything, it doesn't make any sense, and this is not really that nice to look at. What you want to do is to turn this whole thing into, as what we have talked about in chapter 2.1, a modulus argument form. So let's do that. From first principle, it's a bit complicated. There's a lot of algebra, you're gonna get confused, so I am just gonna give you an example. So let's take 1 plus I, multiply that by 3, take 2I. With that, we can find the modulus argument form. To get the modulus, you take the square of the first term and the square of the second term, add them together, take the whole square root. 1 plus 1, well, 1 squared plus 1 squared is 2, and so we have root 2 as the modulus. Then argument, if you take the angle of 1 plus 1 from the origin, and you take a kind of tangent angle 1 on 1, arctan of 1 gives you pi on 4. This is the arc, by the way, so I want to put it into cosine pi on 4 plus I sine of pi on 4. That's the first one. Then we have 3 take 2I. So let's find the modulus, which is 3 squared plus 2 minus 2 squared, which gives us 9 plus 4 gives us 13. So we take the root 13 cos plus I sine. Then we want the angle phi. Let's say let's give it a draw, because it's negative 2I, so this is length 2, this is length 3, this length doesn't matter. So I've got the angle theta, which is the arctan of 2 on 3. I'll just leave it in theta form because I don't have a calculator with me right now. So we've got these two modulus argument form. Make sure you have the entire argument enclosed, because this coefficient have to multiply into both. So we multiply these two. Using just simple algebra, we can tell that if you multiply these two, we get the multiplication of the two modulus, then the multiplication of the two arguments, or argument terms. So let's look at the modulus first. So the answer mod will be root 2 times root 13 gives us root of 26. And in the argument, there are multiple ways of proving this, but I'm just gonna tell you because the proof is too long-winded and I am kind of out of space anyway. What you will get is the argument of Z or Z will be equal to the sum of all the complex arguments of Zi, I guess. So that's in general, if I have theta and pi on 4 as my argument, then the total argument will be pi on 4 at theta, where theta is arctan of 2/3. And this is some compound angle stuff that you can use to prove or show. And so on the graph now, we have something that we can actually work with modulus argument for. So let's say 1 plus I is over here with 1 and 1. Then we have 3 take 2i, so about here, 3, then take 2, minus 2, 3, somewhere over here. So I've got these 2 points. If we add them, multiply them together, again I'm gonna put it into the vector form because it's actually a lot easier to look at. I'm gonna link this to here and link this over here. With that, if we sum the 2 angles, then we should get something, because pi on 4 is clearly larger than arctan of 2 on 3. This is actually negative value because you have to compensate for the clockwise and anti-clockwise direction. So we have a negative value of theta, so there we go. We have a negative value of theta in this certain scenario, and so the sum of pi on 4 at theta will be pi on 4 take away tan arctan of 2/3, which should give us something in the positive quadrant, although it's probably going to be quite small. Then we have to put in the modulus, which is root 26, and I'll be honest with you, I can't do this off the top of my head on this graph, so I'm just going to arbitrarily say that this has length root 26. So what I want you to get away with this part of the kind of lesson is to know that if you add 2 complex numbers, you add the 2 factors, but if you multiply the 2 factors, the 2 complex numbers, you essentially need to think in terms of the angles and the sum of the angles, and the length will be just the straight multiplication of the 2 lengths. So with those 2 examples set, what you can do now is to do all complex manipulations. However, one thing that you need to note is that always go back to the real part, imaginary part system for addition and subtraction, because that's the most straightforward way. And for the multiplication and division, always use modulus argument. It saves you so much algebra methods. It's a lot better. For division, I must clarify, because dividing something is essentially multiplying it by the inverse of, so basically if you divide by 3, you multiply it by 3 to the minus 1. You do the same for division in modulus argument, and so essentially what you would do in division is you divide the modulus the normal way, and the argument, you instead of adding, you subtract the argument. It works exactly the same. And finally, make sure you know how the complex numbers dance on the Argand diagram, because it makes a lot of difference when it comes to interpreting particular results and how the system in general works. Alright then, so after talking through a lot of complex numbers, I guess now it's time for you to do some complex questions. Here I have two questions that you need to solve in algebra form, then plot them onto an Argand diagram. And I'll give you about 5 seconds to pause the video, get yourself some paper and pencil or pens to do this, and I will show you the answer in 5, 4, 3, 2, 1. Okay, so these are the two solutions. Solution 1 is 3 on root 2, 3 on root 2 I, and solution 2 is 11 plus 11i. Turns out they're both on the same straight line with argument pi on 4. And that's just complete fluke. It doesn't normally happen like this anyway. So that's it for this video. I hope you've learned something. If you've any questions, then do let me know in the comment section below, and I will see you on my next one.